Welcome to this video on equilibrium, or as I like to call it, aka funny reaction arrows. And what I mean by that, we'll start by my favorite chemical reaction. Again, the most generic one we can think of. A plus A, or A plus B, equals C plus D. I'm not super fussed about what phases they are right now. We'll talk about that a little bit later. But the idea that reactants make products. And the little letters stand for coefficients, whereas the larger ones stand for chemical identities. And you'll notice this time I've used some funny reaction arrows. That it's a half arrow one direction and a half arrow the other direction. That's because we can think of all reactions as fitting into one of three categories. The first option is to think of a reaction as spontaneously proceeding from left to right, so that reactants make products. And often we'll call that direction of the reaction K1, so that the rate in the forward direction, right? So the reaction is spontaneously going forward. By the way, this is the one you're used to. You would calculate a delta G that's negative. Option 2 is a reaction that is spontaneously proceeding in the direction that we would call right to left. So going backwards of what we're used to, right? That's the back reaction. And we would give that a K-1 to talk about the reaction going from reactants back to products. And by the way, we would have just called this before a reaction for which delta G was positive. We would have called it non-spontaneous. That doesn't mean it doesn't happen. It just means that it's not going in the direction that we think it's going. Now, our third option is that a reaction is not proceeding anywhere. And what I mean by that is that the rate that I'm going forward is equal to the rate at which I'm going backward. So the rate at which I go to make reactants to products is the rate at which the products are turning back into reactants. And I call that state equilibrium. Again, what's equal at equilibrium? Are the rates. The rate at which I go forward is equal to the rate at which I go backward. What is not equal, and I want to stress this so much, is that the concentrations are not equal at equilibrium. So that just means that it's not like the concentration of A equals the concentration of B equals the concentration of C equals D, right? The concentrations are not equal. What it means is that the concentrations, so I'm going to use the square brackets for that, are no longer changing. So if I were to look at a graph of concentration over time, for example, I could imagine, say if we're looking at the concentration of A, I could imagine that I start out with some amount of A, and it's a reactant, so it goes down over time. And eventually it stops going down. It just flattens out. So this is my concentration of A. Let's watch a product now. Let's pick C. And it's a product, so we're going to just assume that we don't start out with any of it. It goes up really fast, and then eventually it too levels out. Now, don't worry too much about the point of the levels. You can actually have graphs where they cross. You can have graphs where one stays high and the other stays low. That part isn't important. What is important is that eventually the graph levels out. We just got done talking about this left-hand region, so everything before the dotted line that I just drew in. This is called kinetic control. So when a reaction's under kinetic control, that just means that the amount of stuff, right, concentration is controlled by rate. On the other hand, when I get to the other side of that dotted line, this reaction is under what we call thermodynamic control. So that just means that concentration is controlled by free energy, basically. And instead of free energy, we're going to use this idea of what's called an equilibrium constant, or a K. And K, big K, is called the equilibrium constant. So when you see big K, you think equilibrium constant. And what it's telling you is it's relating reaction composition, so concentrations, to reaction extent. And when I say extent, we could think of somewhere between 0% and 100%. What that means is all reactants or all products. So if we wanted to think about a reaction coordinate diagram from talking about kinetics before, equilibrium just tells us how far we are along this particular axis here. And the K that we're going to look at today is called Kc. You'll notice that we're coming back to that generic chemical equation, and this time I gave phase labels. I gave aqueous. They don't have to be. We'll break that down in a little bit. But Kc, the little c stands for concentration, right? The way that we define Kc is simply by the concentration of the product to its power, and both products, or as many as there are, divided by the reactants to their powers. Now, unlike kinetics and rate laws, the exponents here do equal the coefficients. So big K's, this does happen. You can turn a coefficient into an exponent, no problem. And so what it's looking for is concentrations. And the phases that you can use concentrations on, you can use aqueous, you can use gas. What you can't use is solid or pure liquid. And so if we ever see those to write an equilibrium constant expression, we just eliminate them. The other thing I want you to know about K is that K is unitless. So we don't have to write any units on any of this stuff, which should make you pretty happy because I'm never going to grade you off for that. There's actually a lot of versions of Kc, right? Eventually we're going to work with Ks called Ka and Kb and Kw when we start talking about acids and bases. Later we're going to work with a Ksp, which talks about salts dissolving in water. When I see you in class next, we'll talk about Kps for gases. Don't worry too much about the letter. They're all done the same way. Products to their powers divided by reactants to their powers. Let's go ahead and look at some examples of how we work with that. And before we go ahead and write our Kc expressions, what I want you to know is that K is affected by temperature. Right? What is it not affected by? It's not affected by amounts of reactant or product, right? The only thing I can change a K by doing is temperature. The amounts of reactants and products actually rearrange themselves around K. So let's practice writing just a couple of them. So for example, I have a reaction here where solid copper 2 carbonate is becoming aqueous copper 2 carbonate. And remember, if I wanted to write a K for this, I would need the reactants in the denominator and the products in the numerator, and I ignore anything that's solid or liquid. So up in my numerator, I have products, and I notice that it's aqueous, which is an OK phase. So I would say that the Kc is equal to the concentration of CuCO3. And I notice that there's a solid here, and so I actually don't write it. I just say over 1. Right? So remember, there's nothing in the denominator because I ignored that phase. What about my next one here? Well, in my numerator, there's a liquid, so I'm going to ignore the water. And I can use the aqueous barium chloride, so it's concentration of BaCl2 up in the numerator. And then down in the denominator, HCl is aqueous, so I can use it. I need a squared for the 2 coefficient. And then barium hydroxide. And it just has a coefficient of 1, so there's an exponent of 1. Now in my third one, up in my numerator, they're both gases, so that's allowed. So I put CO2 and H2 in my numerator, and I put CO and water in the denominator. Again, because the phases are all right. Gases. I can use gases, I can use aqueous. I can't use liquids and solids. I can put numbers onto Ks as well. So if I know concentrations, as in this case, right, if I know at equilibrium a certain set of concentrations between carbon monoxide, water, CO2s, and H2s, I really can just plug in the numbers and try. So remember, my K in general from our last slide was that if I knew the concentration of CO2 and the concentration of H2, those would go up in the numerator and their exponents were 1. And in the denominator, concentration of CO to the first and concentration of H2O to the first. And I can really just put in those numbers. So apparently for CO2, 0.0164. For H2, 0.0164. Down in the denominator, 0.0236. And 0.00240. And really, I am perfectly okay with you leaving units off of this. This is the only time that I'm going to let you do this in this class. It's just because K's have to be unitless. When I put all those numbers together, I find that K is equal to 4.75. The number that K is important because it helps us basically decide the extent of the reaction. So let's return to our generic chemical equation and think a little bit more about that. So just a reminder, right? Generic chemical reaction, AA plus BB makes CC plus DD, and K is concentrations of products to their exponents divided by concentrations of exponents to their reactants, or exponents to their coefficients. What I want you to first notice is that if concentrations can't be negative, K has to be positive. So you'll never get a negative number for K. The other thing that I want you to notice is this is really a ratio. Either I can have similar numerator and denominator, I could have one be larger than the other. And so the tipping point really is in the middle of an idea of K equals 1, right? And then I could have K greater than 1 or K less than 1 on the other side. And so on the right side, we'll start with K greater than 1. We call that a product favored reaction. In other words, the numerator is bigger than the denominator, right? So C to the C, D to the D is bigger than A to the A, B to the B, right? There's more products than reactants at equilibrium. The concentrations aren't equal. I have more products than reactants. And then K is less than 1 is the other idea, right? Reactant favored on this side. And of course, that would mean that AA, B to the B, is bigger than C to the C, D to the D, right? I have more reactants than products at equilibrium. And K equals 1, and actually is really between about 0.1 and 10, right? So within this range, we think of as neither reactant nor product favored. So I've got similar amounts of reactant and product at equilibrium, right? So reactions can either lie to the right. So a reaction over here, we'd also say equilibrium lies to the right, or we could say equilibrium lies to the left. So being able to diagnose that helps us think about what's going on in terms of the extent of reaction. With that in mind, let's take another calculation and try to diagnose a reaction as reactant or product favored. So here's a reaction where we combine two NO2s to make N2O4, and we've got some equilibrium concentrations of NO2 and N2O4. Let's try to diagnose this. Let's figure out whether this is an equilibrium favored or reactant favored reaction or a product favored reaction. So I could start with my K, right? We know that the products to their coefficient power go in the numerator, so just a coefficient of 1, so an exponent of 1. And then in the denominator, I need my reactant, so NO2 to the second power. And I have the numbers, so let's go ahead and put in those concentrations, right? 1.26 divided by 0.0760 squared. And that comes out to 218. And so I notice that K is greater than 1. So I would say that this reaction is product favored. Or I could say that equilibrium lies on the right. If I were to calculate the delta G for this reaction, I would say that delta G would be less than 0, right? We are spontaneously proceeding from left to right if we join that at a certain set of conditions. So again, in this video, we've taken a look at what an equilibrium constant is, how we can calculate it, and how we can use that number to diagnose something about the reaction. You might also notice that I've thrown around delta G a lot, and that's because delta G and K are very much related to one another. So we're going to explore that in a later video.